morning once more. So let's begin with today's topic. Today's topic is on, the very first topic is on network layer protocols and IP addressing. So I will read the foreword for you. So Internet Protocol version 4, commonly referred to as IPv4, is the core protocol suite in the TCP/IP protocol suite. So it works at the network layer in the TCP/IP protocol stack, and this layer corresponds to the network layer again of the OSI reference model, Open System Interconnection. So the network layer provides, look here, the network layer provides what? Connectionless data transmission service. Meaning, I want to send data to a particular destination. I don't need to find out whether they are on or not and to connect with them. I don't need to form a connection before I start sending. I just start sending. Are you getting the point? Yeah. And like, for example, when we are using TCP at the transport layer, you remember the three-way handshake, the TCP three-way handshake? Yeah, you have to form a connection. But at the network layer, you don't need to form a connection. Similarly, when you're sending a parcel to your friend in a different town, it's not the same as you calling them. Are you getting the point? Yeah. They don't have to be at the receiving end, then you just send the parcel and they'll go pick it. So it offers connectionless data transmission services. So a network does not need to establish a connection before sending data packets. So each IP data packet is sent separately. This presentation describes the basic concepts of IPv4 addresses. Then we're also going to look at a concept called subnetting, network IP address planning. I told you about that, and also the basic IP address configuration. So by the end of this chapter, you will be able to, you can help us, Maurice?
Yes, I can read. On completion of this course, you will be able to, 1, describe main protocols at the network layer. The second point says you'll be able to describe the concepts and classification of IP version 4, addresses and special IP version 4 addresses.
Okay, and lastly,
the second last says you'll also be able to calculate the IP networks and subnets. The last point says you will also use the IP network address planning method.
Okay, wonderful. Okay, so we have several subtopics. The first one is network layer protocols. Then we're going to look at IPv4 addresses, then subnetting, then a protocol called ICMP, then the configuration of IP. So we already know what a protocol is, right? Can someone remind us what is a protocol? Yes, Fritz.
Policy.
Exactly. So protocols are rules. They are rules. You can also call them policy. They are rules that specify how the data is going to be formatted and also forwarded. Are you getting the point? Now, at the network layer, we have several protocols that operate there. One of the obvious ones that we've been talking about is the IP. In fact, that is the most commonly used protocol at the network layer. And that is why the network layer is also referred to as the IP layer. So when you hear IP layer, then we are talking about the network layer. Now, we also understand that the network layer is commonly referred to as the layer 3. Layer what? Layer 3 of both the TCP/IP model and also the OSI reference model. Now, the main purpose of the network layer is to provide IP addressing, are we together? And data forwarding, what we are calling routing. Are we together? So IP addressing, you remember last time we said data has to have a logical address and a physical address. The logical addressing is done at the data link layer. The logical address is done at the network layer. So we are going to look at what this is. Now, other than the IP protocol, another common protocol that operates at the network layer is the Internet Control Message Protocol, commonly just referred to as ICMP. Now, we are going to look at ICMP and the functions of ICMP in this particular topic. It's one of the subtopics. But it enables data forwarding through reporting. So we are going to see how. Then we also have another protocol called IPX, or Internet Packet Exchange. Now, with IP, when you talk of IP, we also talk about the versions. We have what you call IP version 4, and we have now what we are moving to, which is IP version 6. The reason as to why we are moving from IP version 4 to IP version 6, it's because IP version 4 have been depleted. It offered about 4.2 billion addresses there, and right now it has been depleted. So that's why we are moving to another version, which offers a larger number. So again, there's an entire topic to do with IPv6. Now, IPv6 is also commonly referred to IPNG, or IP next generation. So anytime you hear someone talking about IPNG, just know that they're talking about IPv6. It is important to appreciate that this resource was created by the Internet Engineering Task Force, IETF, in a Task Force TF. Now, the Internet Protocol. So IP is a short form for Internet Protocol. So it is IP is the name of a protocol file with small content. So it defines and describes the format of an IP packet. The frequently mentioned IP refers to any content related directly or indirectly to the Internet Protocol instead of the Internet Protocol itself. So some of the functions of the Internet Protocol is logical addressing for devices. And number 2, data forwarding of packets. We've already talked about the versions. So data encapsulation. You remember we looked at this. What did we say data encapsulation is last time? Yeah, yes.
The process of adding a header and a tail to a data packet.
Exactly. Very good, team. So the process of adding information either on the header or the tail as the data moves from the upper layers to the bottom layers. That is what we call data encapsulation. So by now we understand that at each layer, the data will have different information because you're going to add different information at each layer, right? And for that reason, at each layer, that particular data, or what we call PDU, is referred to us by a different name at each layer. Are we together? For example, when it's just data at the application layer, it's just called a PDU. Are we together? If it goes to the transport layer and we add a header, TCP header information, then it's called a segment. At the network layer, again, we add an IP header and we call it a packet. At the data link layer, we call it a frame because we add layer 2 information like the source and destination MAC address. Now, finally, the data will reach the physical layer where it's going to be converted into electrical signals or light signals or microwave. And at this layer, we call the PDU or the protocol data unit bits. Are we together? So this process of adding information to the data as it moves from the upper layers to the lower layers is what we call data encapsulation. The opposite, which is now removing when the data gets to the destination, and we are now moving it from layer 1 all the way to layer 5. Then that process is called what? Decapsulation. Now, at the network layer specifically, at the network layer, we add an what? An IP header, an internet protocol header. So we are going to see the contents. We're going to see the contents of that particular header. So this is what we call the IPv4 packet format. IPv4 packet format. Now, it is important to understand, as we saw earlier, even with the TCP header, that an IP header simply is a list of fields that can hold certain information. Are we together? One of the obvious ones that, for example, you expect on an IP header is the what? Is the what? Source, IP address, and destination IP address. See, those ones are expected. But other than those ones, we also have a few others that you need to be aware of. So I'll just explain a few, then we are going to explain the others in detail in subsequent slides. Now, the first one I want to mention about is what we call the version. Can you guess what this field stores? What do you think this field stores? Yeah? Eh? The version of the version of IP that is being used, right? So you said we have IPv4 and IPv6. Yeah. So when the value here is 4, it simply means that we are using IPv4. Otherwise, if we are using IPv6, then the value there is going to be 6. Now the version field is 4 bits long. 4 bits long, meaning when we use Wireshark to look at the IP header, the contents of the IP header, you might not get a value 4, but 4 written in binary. Are you getting the point? Yeah. Now, other than that, we also have the header length. The header length really indicates the size of the IP header. The size of the IP header. Now, look here. Normally, the IP header, the very first, this particular part, all these fields will total to a maximum of 20 bytes. But we also have an options field and a padding field that can vary in terms of size between 0 to 40 bytes. So when we add 20 plus whatever size this is going to be, then that particular value is going to be stored on the header length field. Is that clear? Then the other one is type of service. Type of service. For now, just know that this indeed is used to indicate the service type. Sometimes on a network, we want to give higher bandwidth maybe to the managers, implementing what we call differentiated services. So this field is used to implement what we call quality of service, QoS. Is used to implement what? Quality of service. So we might want to give certain packets higher priorities, so that we're not going to learn about this, but if you do HCIP R&S, you're going to know that sometimes we have to queue packets, and we have different types of queues. So higher priority packets will go to higher priority queues. Are you getting the point? Yeah. So we use that field for that particular purpose. Then we have the total length. The total length is used to indicate the IP, the length of an IP data packet. Then we have these three: identification, flags, and fragment of sets. Identification, flags, and fragment of sets. These three are used for fragmentation and reassembly. Fragmentation is the process of breaking down huge packets into smaller, more manageable chunks. So they're called fragments. So we have to break a 2 GB movie into smaller pieces and send them even through different paths on the internet. Then when they get to the end, they have to be reassembled. Are you getting the point? Yeah. So these three we're going to learn, I think, in the next slide, how they are used. Then we have TTL, very important. We're also going to learn more about TTL. TTL in full is time to live. Time to live. Time to live. And this particular field is majorly used to ensure that we don't have packets that wander forever on the internet. When packets are wandering on the internet, we call it a loop, because it's not going to ever reach anywhere. Are you getting the point? Yeah. So TTL is used to give a certain value to a packet, so that if it will not have reached its destination after passing a certain number of routers, then if that value gets to a 0, then the router that receives that particular packet is simply going to look at TTL 0 and drop that packet. Last time we said, when a router drops a packet, we call it what? Discarding. We use the word discarding. Discarding. So that's how, in summary, the TTL field is used. Then you have the protocol field. The protocol field is used to indicate the next protocol that is going to handle this packet. the next protocol that is going to handle this packet. What that means is we've reached the destination. We've reached the destination. So the data packet moves from the data link layer to the network layer. So at the network layer, when we open up the IP header, we will look at the protocol field to know whether we are going to pass this data to the next layer or to a protocol within the same network layer. So for example, the value of the protocol field can be ICMP, meaning this packet is supposed to be passed to the ICMP protocol, which still operates at the network layer. On the other hand, the value of the protocol field may be also TCP, meaning now it's supposed to be passed over to the transport layer. Are you getting the point? Is that clear? Yes. So that is what the protocol field does. Then the header checksum. The header checksum is used for. We're going to look at it, but majorly for security, just to find out if the packet is intact. The options field. The options field is optional, and you can include some more information on that particular field. Then we have padding. Padding normally is filled with zeros. So that whenever maybe the IP header, whenever the IP header does not meet the required size, so we add zeros to increase the size to the standard size, minimum size. Are we together? Yeah, so that is what the padding field is used for. Okay, so data packet fragmentation. So we want to look at these three. We want to look at these three fields and how they are used. So fragmentation is the process of dividing a packet into multiple fragments. So why do I do this? Sizes of IP packets forwarded on a network may be different. So if the size of an IP packet exceeds the maximum size, if it exceeds the maximum size supported by the data link, by that particular link that you're using to transmit the data, then the packet needs to be divided into several smaller fragments before being transmitted. To achieve that, these three fields, the identification field, the flags field, and fragment offset are used. So the first one is the identification field. It carries a value that has been assigned by a sender host. And normally it is used for fragment reassembly. So it's just a value that has been assigned by the host. Then we have the flags field. Flags field can have the flags field is 3 bits long. The first bit normally the first bit is reserved and will always have a value of 0. Reserved simply means it's unused. It doesn't have a function. Are we together? Yeah. So it has 0. Then the second bit is used to indicate don't fragment. Don't fragment. It can have 1 or 0. 1 meaning do not fragment. 0 meaning fragmentation is allowed. Then the last one is more fragments. more fragments. Again, can have a 1 or a 0. 1 indicating we have more segments. We have more segments that are coming. When it's a 0, it means this is the last segment or fragment. So why do you think we need to indicate the last one? Why do you think we need to indicate the last fragment? So that we can alert the destination to start reassembly. Are you getting the point? Is that clear? Yeah, so what simply this means is this, you'll have a value like 0, 0, 1, 0. And this means that, what does a 1 mean for here? It means don't fragment. What does a 0 mean for this one? It means this is the last fragment. Are we together? So that is how the flags field is used. So just graphically, you're seeing we're having data, but we have to break it down into fragments. Are you getting the point? So each fragment will have the identification flags and fragment offset. Now, the last field that is used for fragmentation is fragment offset. It is used for fragment reassembly. How? It indicates the relative position of a fragment in an original packet that is fragmented. It indicates the relative position of a fragment. The relative position of a fragment in an original packet that has been fragmented. So by that we mean the fragment offset. So for example, this is the, oh sorry, thought I had clicked that. For example, this is fragment number 1. This is a fragment number 2. This is fragment number 3, like that. Now, in an actual network, you might find that all these fragments are going maybe to pass through different paths. Are you getting the point? But at the destination, it is the fragment offset that is going to rearrange these fragments and reconstruct the data. Is that clear? Yeah, so that is what the fragment offset is used for, simply for labeling the packets or the fragments. So the time to live, expect a question in the exam. It has to be there about the time to live. And one of the first things I tell my students when I talk about the TTL is that time to live is not associated with time. Are we together? It's not associated with time. It is not associated with time, as the name might suggest. It is used to specify the number of routers. Simply put, used to specify the number of routers that a packet can pass through. So what happens when a packet passes through a router, the value of the TTL is reduced by 1. Now, if the TTL value is reduced to 0, what happens? The data packet is discarded. Now, you might ask, this value that is reduced by 1, where does it come from? Where does it come from? The answer is at the host. As the host creates the packet, it's going to include a particular TTL value. Different protocols might have different values for the TTL. Are you getting the point? For example, here, the TTL value for this packet is 255. When it passes one router, the TTL value becomes, and when it passes another, it becomes. Now, if it reaches the router that is connected to the destination, then the packet is going to be delivered to the destination. Are you getting the point? But if this particular packet passes how many routers? 255. The 255th, is that correct English? The 255th router is going to reduce that value to 0. And by doing that, it's going to discard that packet. It's not going to forward that packet further. Are you getting the point? So why? Why the time to leave? Why? Why the time to leave? Now, the time to leave, as I said, is used to prevent network congestion caused by loops. So when a packet is just wandering on the internet or the network and not getting to the destination, then we call it a loop because it's just looping around. Now, that is just one packet. What if we have 2 packets, 3 packets, 100 packets, 1,000 packets looping? They're going to consume all the resources on the network. And the network is going to be congested. And the network is going to collapse. The network is going to collapse. So loops are bad in a computer network because they're just going to overwhelm the resources, and in fact, the routers are going to hang, the switches, they're going to hang, and they're going to maybe restart or something. And service is going to deteriorate because now they are processing useless packets. So by having the TTL, we cannot have loops, thereby preventing network congestion. Now, the other thing you need to know is that that particular router that is going to discard the packet is also going to send an ICMP error message to the source. See, that packet will have the source IP address on the IP header. So it's simply going to read the source, then it's going to send a message, hey, you guy, my guy, we can't find whoever you're looking for. Are we together? So we're going to look at those specific ICMP error messages in a moment, and you're going to appreciate this fact. But please don't forget, we've said a few things about the TTL, that it is reduced by 1 every time it passes a router, that the initial value is determined by the host, that that particular router that decreases that value to 0 is going to do 2 things. Number 1, it's going to read the source address and send back an error message, ICMP error message, to the source. That error message can be host unreachable or network unreachable and others that we're going to see in a while. After sending that ICMP error message, it's going to discard the packet. So don't forget that. TTL. The protocol The protocol field identifies a protocol that will continue to process the packet. Identifies a protocol that will continue to process the packet. That protocol might be a network layer protocol like ICMP, or it might be an upper layer protocol, transport layer protocol, TCP or UDP. So normally at the protocol field, we will have a value 1 if we are supposed to pass this packet to ICMP. We will have a value 6 if we are supposed to pass this packet to TCP, and 17 if we are supposed to pass it on to UDP. Okay, so that is it about the protocol. Anyone with a question so far before we move to IPv4 addresses?
Yeah, teacher, I had raised my hand. Sorry. Thank you.
Oh, I can't see that. Maybe it's because of.
Oh yeah.
Okay, go ahead. Go ahead, Maurice.
Yeah. Is time in any way related to these protocols, especially the TTL? Because you've also said that it is not in any way related. But according to me, I think it should be related, because there's a time, there's that time that a packet should take before it can be discarded actually from the network.
Not really, not really. In fact, the IP header does not have any field that is related to time. The IP header does not have any field that is related to time.
Okay.
And time to live is not related to time at all. It's just a value that will be inserted there by the host, by the source, and reduced by 1. So it's not time.
Okay.
It's not in seconds, it's not in hours, it's not in minutes. No.
Fine. That's okay.
Okay.
That's okay.
Thank you. Let me go to you, Kellen. Then I can come back to you, Solomon. It will come up again. Oh, hello timer. Oh, maybe he's talking about those timers. Now, those timers, we're going to look at some timers when we look at a protocol called OSPF. So OSPF, on its header, it has fields that are related to time, about 3. So we're going to look at that. But on the IP header, no field is related to time. Absolutely. Okay. Yeah. But oh, DDoS. Oh. So Solomon is asking, in a DDoS is denial of service attack. Denial of service attack. Does the hacker use loops? Denial of service attack. DDoS, denial of service attack. So how denial of service attack works is a hacker sends so many packets to a particular host so that it becomes congested and it crashes. Are you getting the point? So he's just asking, does an attacker use loops? So I think the answer to that question is no, because normally you configure your network to deal with loops, to avoid loops. So how the denial of service attack works is this particular guy fakes either especially the source or destination IP address. So for example, I send all of you messages with a fake IP address for Solomon as the source IP address. So I don't use my own source IP address. I use Solomon's. And I tell all you guys, hi. And all you guys now reply at the same time to Solomon, hi. So Solomon is going to be overwhelmed with all those messages. So you're not replying to me because I faked my source IP address. So that's how a denial of service attack really works. Yes, Lou.
Question on time delivery.
Or question on TTL.
Does it, okay, you don't know, like, several users, the use of the efficiency of data delivered. For example, we see 55 users, the data get discarded. Nonetheless, the data get transmitted. That is first question. The second question.
Just come up again on that first one. Is having many routers
reduce the efficiency of data delivery?
The efficiency. Because eventually it's going to be dropped.
Yeah, you have 255 routers, but data is get discarded. You have less get delivered.
Not really. Not really. Let me just answer that one. You see, in an actual network, when you talk of 255 routers, you're simply meaning that your packet now is on the internet. It's not like you have an organizational network and you have these 255 networks. So your packet has actually gone out and is trying to be routed from one router to another until now. Third world country problems. Power is out on this end. So let me just stop the recording, then we can have a discussion. Let me just post the recording.
Okay, so now we look at IPv4 addresses. So what is an IP address? An IP address identifies a node on a network. So we are saying an interface on a network, an interface. Now, please be informed, an interface is what we also call sometimes a port. Now, in this particular case, a node does not represent a computer, but an interface. It does not represent a computer, but an interface. Because a computer or a layer 3 switch or a router, we can have more than one interface or ports. Is that clear? So we do not assign an IP address. We do not assign an IP address to a computer or a switch, but really we assign that to an interface. You remember when we were talking about data link, we talked about the NIC, the network interface. Okay. So each interface or each NIC comes with an interface. Yeah. So IP addresses, they're used to forward IP packets on the network. They're used to forward IP packets on the network. So what what happens is you have a guy here that wants to send some data, going to send it to a layer 3 device. Then the layer 3 device is going to route the device over the network until eventually it gets to the destination, for example, like that. So an IP address identifies a node on a network and is used to find the destination for data. So to assign an IP address to a device, then you have to configure an IP address for the interface on the device. So let's look at the format. How does an IP address look like? Some of you might have seen it. Some of you maybe have never seen an IP address. But let me just write for you the first one that is here, 192.168.10.1. So that is an IP address. That is how it looks like. Now, we write it in what we call the dotted decimal notation in 4 parts to make it easier to remember and to write. Now, an IP address is made up of 32 bits. So we say that it is 32 bits long. What that means is if we convert this into binary, then normally we write it as 8 bits, 8 bits, 8 bits, 8 bits. So if you do 8 times 4, then you'll get 32. So at each section, because it's 8 bits, it simply means at each section, it can move from 0 all the way to 200 and 255. So how do we get that? For those ones who know story a binary, 2 raised to power. Where is it? Where is power here? Where is the up arrow? I can't see it. Oh, it's here. 2 raised to power 6, right? You're going to get 256. So if you start counting from 0 to 255, then you get 256. Is that clear? Yeah. So to understand IP addressing and planning, you need to have some basic understanding of the conversion between decimal and binary number systems. Let me see by a show of hands, how many of us understand the conversion, how to convert binary to decimal and vice versa? Let me see. How many don't know, have never met? So all of us know, right? Huh? Online, Alain, Maurice, Peter.
It's
Do we
been
know how
long
to
on my side.
Yes.
It's been long. I think I did that a long time ago, close to 2010. So I might have forgotten.
No. I know.
Teacher, we can't hear you. I think maybe it's an issue from your side.
Oh, hello. What about now?
Yes, now we can hear you. But from the time I had actually said it's been long, I've not heard you.
From the time I said, what's the last thing you had?
From the time I told you, it's been long since
Okay.
we did the conversion.
Oh, okay. Sawa. So we've said that during your own time, you try and learn about the conversion. So what I was saying now is that because each section can move from 0 to 255, the very first address in the address range is 0.0.0. And the very last one is 255.255.255.255.255. Now, the total number of addresses that we get from IPv4 is 2 raised to, how many bits do we have? 32. So how many addresses do we get from this? What is 2 raised to power 32? Huh? 4 point what billion? 2 raised to power 32. What do we get? Yes? So normally it is about 4.3 billion addresses. So in the early development stage of the internet, this was a massive number. And the creators of IPv4 thought we will never exhaust this address space. But around 2011, IPv4 addresses were depleted because more people have connected to the internet, especially because of the World Wide Web, and more people have devices. So right now, the world is transitioning from IPv4 to IPv6. Okay, maybe I can give some basics about binary conversion. Maybe I can give the basics. So we call this binary because we know bi means 2. So it only uses 2 digits, a 1, can I say or and? It uses 1 and 0 only, right? Otherwise, the number system that we are commonly used to is called the decimal number system, which uses the numbers 0 all the way to 9. So 10 numbers. That's why it's called decimal. So when you write 192, that's a decimal. 168, 10. It uses digits between 0 to 9 to create its numbers. So normally you can't be able to convert between binary and decimal and vice versa. How you do it, it's very easy, by the way, and interesting. How you do it, for example, you have the value, can we use 10? You have the value 10, you want to convert it to binary, decimal 10. You want to convert it to binary. So what you simply do is you divide this value by 2. You divide it by 2, then note down the remainder. Are we together? So 10 divided by 5, 10 divided by 2 is 5. Remainder 0. So hiyo 5 ndio inakuwa the next. So we again divide 5 by 2. What will be the remainder? 1. And what is 5 divided by 2? It goes there 2 times, right? Then again, we divide that one by 2. The remainder will be 0, right? So how many times does 2 go into 2? It goes once, right? That's how. So what is 1 divided by 2? It doesn't go, right? What remains? Huh? See, 1 remains. Eh? Are we together? Ah, eh? What remains? See, 1 remains. 1 divided by 2 is 0, right? It doesn't go. So what remains? 1, right? So that is where that stops. Eh? Are you together? That is where that stops. So what happens is now to write this into binary, you start writing these remainders from the bottom to the top. So 10 in decimal in binary is going to be 1, 0. Oh, sorry. 1, 0, 1, 0. Is that clear? 1, 0, 1, 0. So let me show you now how to go back. How do we go back from binary to decimal? Binary to decimal. So, how did I write that? Okay, so binary to decimal. Oh, it's overwriting. Binary to decimal. So we have 1, 0, 1, 0. We want to take it back to 10. Are you together? So normally, each position of the binary has a value. Are we together? The very first position is position number what? And we start giving them the number from this side. Eh? So the very first position is 0, then 1, then 2. Oh, boy. Let me just write. This will be 3, 2, 1, 0. Are we together? Are we together? So what we do is that we raise 2 to each of these positions. So 2 raised to power 3 is going to be, is it 8? Ah, did I do this correctly? Yes, yes. It's 8, right? Then 2 raised to power 2, 4. 2 raised to power 1, 2, right? 2 raised to power 0, 1, right? Now, once we've gotten this, we multiply it by these values, then add them together. So what is 8 times 1? 8. What is 4 times 0? What is 2 times 1? 2. What is 1 times 0? 0. So after doing that, then we add 8 plus 0 plus 2 plus 0. And we end up with 10. So please find time and learn how to do this conversion, but it shouldn't give you much problem. It's not very difficult. Now, it might seem a little bit tricky at first, but with binary, with this, it's a little bit easier. Maybe just something else that I need to mention. That I haven't there is that whenever you write a value in binary, for example, we know now that 10 is 1010. Whenever you write it like that, adding zeros to the left does not change the value, does not change the value of that binary number. Is that clear? Adding 0 to the left does not change, because if we start counting now, you have this as position 7, this on 6, 5, 4, 3, 2, 1, 0. So if we raised each of this to power 2, 2 raised to power 7, you're going to get 128, right? 128, right? But when you multiply 128 by the position, which is 0, you're going to get a 0. 2 raised to power 6, 64, times 0, 0. 2 raised to power 5, 32, times 0, 0. 2 raised to power 4, 16, times 0, 0. 2 raised to power 2, times to power 3, 8, times 1, 8. 2 raised to power 2, times 0, 0. 2 raised to power 1, you get 2 times 1, 2. 2 raised to power 0, 1 times 0, 0. So you see, if you still added this, you're still going to get 10. So adding zeros to the left does not change the value. Now, I'm saying that because sometimes we might want to represent binary values in 4 bits or, for example, in 8 bits. A bit is a 0 or a 1. Are we together? So normally in computing, most of the time we represent data using bytes. A byte is 8 bits. So with IP addresses, of course, since they move from 0 to 255, each portion is made up of 8 what? 8 bits. So simply means that the very first bit at that space 2 raised to power 0, then to power 1, all the way to 2 raised to power 7. So if we want to convert this binary number into decimal, then we are going to multiply like the way we've been doing. 2 raised to power 1 to power 2 raised to power 0 times 1 times 0, like that, like that. So until at last we're only going to add what? We're only going to add 128 plus 64 to get 192, because all the other bits are 0. So even if we raised and added them, they're still going to be 0. So that's how normally we convert between binary and decimal. Okay, so yes. Who has a question? Yes.
About that conversion,
Yes.
On the exams, just for the knowledge, on knowledge.
Peter,
can it be tested?
Peter, can you move closer to your mic, or maybe can you type in your question? I'm not sure whether you can be able to use messages, because I can't hear you well.
Let me type.
Now we can hear you better. Ebu, go again. Okay. I think he's typing, so let me just open up the chat. Okay. As he types, we can move on. Now, the other important thing that you need to understand is the address structure. Now, before I talk about this, let me talk about my mobile number structure. Now, 254 plus 254, then 729, then 385557, like that. So that's my mobile number. Now, what does what does plus 254 represent? Plus 254. Huh? It's called the what? The country code. Specifically, this one is for Kenya. What does 729 represent? Huh? The network, right? And this one particularly is for Safaricom. Then what does 385557 represent? Huh? My unique number, right? Can we have someone else having that number on 729? No, right? It's my unique number that identifies me. Similarly, IP addresses are structured to, number one, identify the network, and to also identify the individual host on the network. So here we have a network part that identifies the network that that computer belongs to. Then number two is the host part, which identifies the host and is used to uniquely differentiate hosts on a network. Now, we have what is called a network mask. A network mask is also commonly referred to as a subnet mask. Subnet mask. So when you hear of network mask or subnet mask, it's the same thing. Now, the network mask is a 32-bit long number that is written in dotted decimal notation, just like the IP address. What happens with the mask is that it consists of consecutive ones and consecutive zeros. Are you together? Now, look, this is how we write a mask. For example, 255.255.255.0. So if you convert that into binary, you get consecutive ones. Then after the consecutive ones, you get consecutive zeros. Now, normally, we use IP address together with the mask in order to identify which part of the IP address represent the network and which part of the IP address represent the host. So where we have consecutive ones, then that part of the IP address represent the network. Are we together? So here, all these bits on the IP address represent the network because they match with the consecutive ones. On the other hand, the remaining bits will now represent the host. Will now represent the host. I think the question has been typed in by chat. Will there be any question on binary and conversion? No. There won't be any question. Peter, there won't be any question about the conversion, but you need to know it because they'll ask you. You're just going to see that we are going to learn a few concepts here that will need you to at least understand how to convert between those two. So it's a skill that you must have as a network engineer. But you won't have any question telling you to convert, no. But for you to answer certain question, you have to know the conversion. Okay, so I hope this is clear. about the network mask or the subnet mask? Hmm? Yes, you have a question. Uh, uh. Yes, yes. We have other network masks. We have other standard network masks. You're just going to see them right now. And we also have what we call variable length subnet mask. We've said that a network mask is also called subnet mask. So we also have what we call VLSM, variable length subnet mask. So we can also vary the number of ones and the number of zeros in order to either increase the number of hosts or reduce them, or increase the number of networks or reduce them. So we're just going to see that just now. Now, whenever we configure or write an IP address and its mask, we can write it in one of two forms. Normally, we can write the mask in full, like 255.255.255.0, or we can use what we call the mask length. The mask length. The mask length is simply the number of ones. The number of ones in the mask. So by that, what will be the mask length for 255.255.255.0? We have 24 ones. So we can write in also what some people call the slash notation. We can write an IP address using the slash notation. So this is what we're calling the slash notation. This one. We write the IP address, then we write a slash, then we write the number of ones of the subnet mask or network mask. Is that clear? Is that clear? Yeah. So please don't forget that we use the network mask to distinguish the network part from the host part in an IP address. So anytime you configure an IP address, you must also include the network mask. Okay, so let's move on.
There's a question, Walim.
Oh, let me check. Okay. During the exam, especially for us on distance portal, shall we be allowed to do some rough work, especially on this kind of conversion? Is a calculator allowed in the exam room? It depends. Which calculator are you talking about, Maurice? Is it the calculator on your phone? The answer will be no, right? Because you can't use your phone. Then most of the time with those exam systems, you can't be able to shift from that window to any other part of your computer. But you can have a calculator. But generally, they don't bring questions where you will really struggle to convert. They don't bring questions where you will struggle to convert. And as we do several examples, you might find it a little bit easier to convert. So don't let it disturb you, really. Okay, thank you. So IP addressing, the network part of an IP address is also referred to as the network ID, network identifier. Why? Because it indicates the network where the host is located. Are you together? Yes. Now, the host part is also referred to as the host ID because it identifies the specific interface within a network. The specific interface within a network. Now, we know that with network addressing, we have to do the addressing both at what? layer 2 so that the data can be transmitted via the data link, and we also have to do addressing at layer 3. So normally, you do layer 3 addressing when you want data to be able to move. I'm just saying that, but it's not very accurate, and I'll tell you why. But you do layer 3 addressing when you want the data to be routed from one network to another network. Are we together? Otherwise, if computers are in the same network, really, you do not need layer 3 addressing. Is that clear? And that statement is wrong. What I told you is wrong. What I told you is what? Is wrong. Are we together?
I was also about to ask a question.
Uh-huh.
Hello?
Uh-huh.
Yeah, assuming that the likes of MMU, having several routers, actually, layer 3 routers.
Yes.
And let's say the admin, that router between admin and the students, that level, we've got 2 other 3 layers, and I mean levels in terms of the routers, where students are not actually allowed to access, let's say, the finance part and all this other stuff. So does it mean that you should not actually have that IP addressing?
Did I really get you clearly, Maurice? What is he asking?
Just wanted to ask her and confirm with what you just said, although you've said it's wrong anyway. Yeah. But I wanted to know, should we have a router between the finance and another router, let's say the engineering section students and all that, where they're supposed to
files. Yeah. I've understood your question. Do we need a layer 3 device between different network segments when we are dividing the network? So we're going to look at what is called subnetting, breaking a big network into different networks. So we're just going to look at that. And whenever we do that, then we need a layer 3 device in order to route packets between the finance to students and vice versa, subnets. So subnet is simply subnetwork in full. Are we together? So why I said that my explanation is wrong in terms of you at layer 2, you don't need an IP address. It's wrong because you must have an IP address, because that IP address is what is used to learn the MAC address of the destination. That IP address is used to learn the destination MAC address. So even on the same network, if you want to speak to someone on the same network, you still must configure an IP address. Is that making sense? So have we learned about ARP yet? Did we learn about ARP? We learned about ARP. We learned about it, right? Address resolution protocol. ARP is used to learn MAC addresses, right? Yeah, to learn MAC addresses and associate an IP address to a MAC address. Yes, I remember we did this. So for ARP request to be sent out, so you must know the IP address of the destination. In fact, when you're sending an ARP, you're asking the question, who owns this IP address? Then whoever owns it within that local area network will reply with their own MAC address saying, hey, I'm the one that owns this MAC address. Then now you can be able to send that person information. So what we are saying is to send data across networks, you must have an IP address. Now, normally, that device that is used to forward data between networks is commonly referred to as a what? As a gateway. And a gateway can be any layer 3 device. So it can be a layer 3 switch or a router. Is that clear? Now, on that layer 3 device, you are going to configure an IP address for this interface that connects this particular network. Are we together? You're going to configure an IP address for this interface. Now, this particular IP address that you give this interface is what we call the gateway IP address. And all your devices need to have the gateway IP address. They need to be configured with the gateway IP address, meaning, hey, if you want to communicate to anyone outside this network, then send that packet to this interface. Then this guy will now handle it from there going forward. So have we understood about the gateway and about the interface? Are we together? So normally, in fact, most of the time, on that address range, we give the gateway the very first IP address. So for example here, we can configure it with maybe 10.0.1.1/24. So all the devices need to know the gateway IP address for them to be able to communicate outside this network that they are in. So I hope that is clear. Okay, I think I'm moving slowly, so I'll try and move a little bit fast. We have what we call classful. We have what we call classful addressing, and we have what we call classless addressing. Classful means that the IP address are classified into classes. The classes range from class A to class E. Class A to class E. So, of course, this was done in order to easily manage these particular address resources. Now, you can see, for example, class A covers the range 0.0.0.0 to 127.5.5.255.255.255. Class B begins from 128, which is the next address from there, up to 191. Class C begins from 192 all the way to 233. Then class D begins from 224 all the way to 239. Then lastly, we have class E, which begins from 240 all the way to the last IP address. Now, it is important to understand that only class A, class B, and class C can be assigned to hosts. On the other hand, class D addresses are used for what we call multicast. You remember we said that we have unicast messages, which is one-to-one. We have multicast messages, which is one to a group. And we have broadcast messages, which is one to everyone. So when we say that this range is used for multicast, it simply means, for example, if we have 6 routers and we've configured OSPF. OSPF is a protocol, dynamic routing protocol that is used to LAN paths. We're going to look at it next week. So if we have only configured 3 routers to communicate using OSPF or to LAN networks via OSPF, then they are going to listen for OSPF packets on a particular multicast IP address. For OSPF, normally it's 224.0.0.5 and .6. Are we together? So that's how we use multicast. So only those three will be able to listen for OSPF packets. And those OSPF packets will have a destination address of 224.0.0.6, for example. So if we've enabled OSPF on that router, then it's going to open up that OSPF packet. So that is what we call multicast. Are we together? Then the last one is used for experiment, class E, is used for research. Is used for research. Now, one easy way to remember the address ranges. So in an exam, you'll be given a question like, you'll be told that 19 oh, sorry, I'm not even writing. You'll be given something like 192 dot maybe 3.4, like that. Then you're asked, where does this address, to which class does it address belong to? So one way to know very fast where it belongs to is simply change this to binary. You just change the first one to binary. So you change 192 to binary. So once you do that, this is how you determine the class. Normally, with class A, the very first bit has to be a 0. So if you convert to 192 and the very first bit is 0, it's in class A. Are we together? If it is 10, then it is in class B. If it's 110C, 1110, E, 111, 4 bits there, then it is a class E address. So that's one of the easiest ways to know where a particular IP address, which class a particular IP address belongs to. Okay, now the other important concept that you really need to understand is the concept of default subnet mask. Please don't forget this. Default subnet mask. So the default subnet mask for class A is 8/8, meaning only the first 8 bits represent the network. The other 24 bits represent the host bits. So for class B, it is /16, meaning the first 16 bits represent the network, the remaining the host. And class C, /24, meaning these bits represent the network, while the remaining represent the host. So with that, you can calculate the number of hosts you can get from a class A IP address. How to do that? 2 raised to power what? Huh? For class A, 2 raised to power 24. Is that together? Is that clear? Class A hosts. 2 raised to power 24, right? So that is what we said. Did we say that? 24 imetoka wapi? Oh, we are talking about host bits. 8 is network bits, eh? Then the remaining is host bits. So they are 24. Are we together? Class B. Two raised to power? Exactly, 2 raised to power 16. And lastly, class C, 2 raised to power. So you can see this guy will give you how many addresses? 256. 256. Okay, so let's move on. So address types, we have several addresses that you must be aware of. One of the address is what we call the network address. Is what we call network address. Now, the network address is used to identify the network and cannot be assigned to an end device. Let me repeat that again. The network address is used to identify the network and cannot be assigned. It cannot be assigned to any host. It cannot be assigned to any host. So that is what we call a network address. Now, normally with the network address, the host bits, if you convert the host bits, because you see this one is a /24, right? So normally, if you convert the host bits into binary, you are most likely going to get a contagious zeros, all zeros. Are you together? Sawa. So like 192.168.10.1/24. So this one is the network address, and we're going to see how to calculate others. So sometimes you can be given an IP address and they ask you to find the network address. So I'm going to show you how to do that. Then you have a broadcast address. As the name suggests, this one is a special address that is used to send data to all hosts on that particular network. Send data to all hosts. Now, with the broadcast address, if you convert the host bits, you're going to get a contagious ones. So just like the network address, the broadcast address cannot be assigned to any interface. Now, what can be assigned to an interface is what we now refer to as the available what? Available addresses. Now, how we calculate the available addresses is like this. How we calculate the available addresses is like this. 2 raised to power n minus 2, where n is the number of host bits. Where n is the number of host bits. So if you get an IP address and it is a /24, then what will be our n? Hey, if you get an IP address like this one that we have been given here, /24, so what will be our n? What will be the number of host bits? See, 24 means those are the network bits, right? So how many bits do we remain with for the host? 32 minus 24, right? Which is 8, right? 8. So we have to remove 2. Can someone tell us why we are removing these 2? Why are we removing? Yes, Kellen. Exactly. We are removing the very first address and the very last address. That very first address on that range is what we call the network address. The very last one is what we call the broadcast address. So we are removing those 2. So that's why we are doing minus 2. So when we do that, we get the available addresses. These available addresses are what we can now use. These are what we can use to assign to our computers and routers. So you can see that this is an example of the network address. This is the example of the broadcast, and you can start assigning. You can start assigning from .1. Are we together? You can start assigning from .1 all the way to what? Available addresses in this one is 168.10.1 all the way to what? See the broadcast minus 1. Ama? So you say the broadcast ndio ya huko chini kabisa. So we can issue all the way from .1 to 192.168.10.25. Is that clear, by the way? Or it's confusing? Huh? Is that clear? Yeah. The first available address is the network address plus 1. The last available address is the broadcast address minus 1. It makes sense, right? Hey, talk to me. It makes sense. Kwani mnakaa ni kama mnahang? Okay, sawa. So let's move on. Okay, so here we just want to show you how to calculate the network address, how to find the broadcast address, how to find the total number of addresses, how to find the number of available addresses, and also how to identify the range of available addresses. Just something like what I've shown you, but now well organized. Now, if you get an address like this, look here, we have this address 172.16.10.1/16. What does /16 tell you? These two parts are used to represent the network. Then these parts can be used to identify the hosts. So what happens? First thing you do, you convert the IP address and the mask, network mask. You convert them into binary. Are we together? You convert them into binary. Now, to get a network address, you do a logical AND between each bit of the address and the mask. You do a logical AND. Do you guys know what a logical AND is? Logical AND. It's easy. It's very easy. So you don't really need to think a lot. So this is the rule for logical AND. 1 and a 1 is a 1. A 1 and a 0 is a 0. 0 and a 1 is 0. Finally, 0 and a 0 will give you a 0. So with the logical AND, it can only be a 1 if both bits are 1s. Otherwise, it's a 0. So that's the logical AND. So let me show you how we are doing it. So you can see that we are doing 1 and a 1 to get a 1. Then we do 0 and 1 to get 0, right? Are we together? Now, just to make it a little bit quicker, we know that the mask will have consecutive ones, right? For the network part, eh? To be precise, for this one, it will have 16 ones, right? Eh? So anywhere where we have the consecutive ones, it simply means that after doing the AND, we're just going to get the same thing, right? Are we together? If you compare all this part and all this part, it's the same thing. because a 1 and anything else will just give you that other value that you've ANDed it with. So, Richard, are we together? Okay. So finally, we also know, look here, finally, we also know that after the consecutive ones, we are going to have consecutive zeros for the host bits of the mask, right? And when you AND anything with a 0, what do you get? When you AND anything with a 0, you get zeros. So you will get that our network, that one is very small. Let me just write it. Our network ID is 172.16.0.0. If you convert now that into binary, /16. Is that clear? So that's our network ID. So you get a network ID by doing a logical AND between the IP address and the mask. And it's very easy, by the way. Sometimes you don't even need to, you just look at it and write the, in some instances, and write the network address. So that will be our network address for that IP address. Okay, allow me to clear this so that we can look at the broadcast. With the broadcast again, you see we have this. We have this boundary, right? This boundary simply separates the network part from the host part. So to get the broadcast, I don't know whether you guys can see this, but it says the broadcast address is obtained with all host bits set to 1. So you simply convert all host bits to 1. When you convert all host bits to 1, then you get the network address. So if you convert now this broadcast address, if you convert this, now it becomes 172.16.255.255 slash what? 16, right? So that's how you get the broadcast address. The next one is the total number of addresses. Of course, total number of addresses is 2 raised to power the number of host bits. So the number of host bits is 16, so 2 raised to power 16. The number of available addresses, 2 raised to power n minus 2. Very good. Then range of available addresses. See, I've told you how to do that. Range of available addresses. For the first address you can assign to a host, you simply add 1 to the network address, right? Yeah? So it's going to be 172.16.1.0.1/16. The last one, you subtract 1 from the broadcast. So you're going to get 172.168.255.254/16. So that's how you get the range. So again, expect a question on this one. Okay, so we have a quiz here. We have a quiz that I want you to attempt. Then you can give me the answer. You make sure you find all this. I want you to find the network address, broadcast address, number of addresses, number of available addresses, and range of addresses. So you've been given the IP 128.20.10/8. So can we work on that? Let's find, we want to find the network address. We want to find the broadcast. Hey, we are doing this, by the way, in discussion. So join up. Number of IP addresses, available addresses, and lastly, range of available addresses. Hey, let's join up. Okay, so that's enough. That's enough. So let's do this. Hey, let's do this together. Let's do this. So, as I've said, to get the network address, you can do the logical AND. But the simplest way is to change all the host bits to what? To zeros. So if you do that, here you get 10.0.0.0/8. So that is the network ID, network identifier. You cannot assign it to a host. Then the rule for getting the broadcast, you change all the host bits to 1, to ones, right? So you'll get 255.255.255/8. Number of IP addresses, how many host bits do we have? 24, right? Available addresses, 24 minus 2. Range, what will be the range? 10.0.0./8, right? All the way to 10.255.25/8. Which one? Which one? For the range. For the range, we said the very first address in this network that you can assign is .1. Maybe can I use my mobile phone number? If, for example, 0729, if 000 could be used to identify the network, then the very first number that can be given to anyone is like that. And the second one, 02, 03, and so on and so forth. So here, we're just adding 1 to the very last portion there, right? Then we are subtracting 1 from the last one to get the very last IP address on that range. So +1 minus 1 to get the range. Thank you for that. Okay, those that are online, are you there? You've been quiet. Can you hear me? Maurice, can you hear me?
Yeah.
Okay. How has been the exercise on your end, Peter?
Available address. Yeah, at least I've now known calculate the range.
Okay, sawa. Haya, tuendelee. Allow me to clear. Is that okay now? Yes, please. I'm sorry. Is it on this slide? The one I've done here on the board? You're saying that? Sorry, just a moment. I think someone's mic is on mute. Elaine, you have a question? Just a moment. Sharon.
Yes.
Yes, Elaine.
Ask a question.
What?
Hello. Hello.
Yes, go ahead. Go ahead, Elaine.
Dennis.
Oh, it's Dennis. Okay. Go ahead, Dennis.
I want to know if the CRD notation can be used to find the network address. like
if the what can be used to find the network address?
the CRD notation.
I'm sorry.
CRD notation.
Can you type it? I can't quite get you clearly.
Okay, please.
Okay, thank you. Just type it. Okay, Sharon, unasemaje? Unaweza ongea kwa sauti kidogo ndio nikusikie vizuri. Ehe. The first two? Let me just check. Okay, please answer. Hello, let me just pause for a moment. There's a question I'm trying to understand here. So just a moment. Okay, so let's move on. I haven't seen your question, Dennis. Did you type it really? Dennis? I haven't received your question yet.
Yes, I sent to the group.
Yes?
I sent to the group.
Or in the WhatsApp group?
Yeah.
Oh, okay. Let me check. Sorry. Okay. I just wanted to know if the CIDR notation can also be used to determine the network address, like for the case of this. Okay. So just hold on a little bit, Dennis. We are going to look into CIDR just now, classless interdomain routing. So we're going to look into it just now. Okay. In order to reduce, listen, please concentrate. In order to reduce the rate of depletion of IPv4 resources, they had to introduce some measures. One of those measures that was used to reduce the rapid rate of depletion of IPv4 addresses was to introduce what we call private IP addresses. So within each class, certain range of addresses were reserved and were used or were set to be used as private IP addresses. Now, why they are called private is because they can only be used within a private network. And that means that they can be reused on different private networks. Is that clear? So that is what we call private addresses. So the same private addresses can be repeatedly used on different private networks. So for example, one of the most commonly used private addresses is the class C. The class C ranges 192.168.0.0 all the way to 168.255.255. But the 172 range is also the class B private address range, and the 10.0 yote 255.255.255 is the class A range. So expect a question whereby you're given an address and you're asked whether it's a private or public address. Now, you need to understand what a public address is. The remaining addresses are what we call public addresses. Normally, public addresses are carefully managed by the Internet Assigned Numbers Authority. So normally, they allocate different continents. For example, I told you for Africa, it's Africa NIC, Afrinic. For Africa, in fact, Africa is the only NIC that excuse me is the only NIC that has a few IPv4 addresses left. So Afrinic gets these resources from IANA. IANA will assign certain blocks of IP addresses. So normally they're assigned in terms of blocks. Then after IANA assigns Afrinic, then Afrinic is going to assign these addresses to country level NICs. Then the country is going to assign them to ISPs in terms of blocks. So that's why using an IP address, we can be able to know your location. Now, it is public IP addresses that are used to access the internet. It is public IP addresses that are used to access the internet. So you cannot use a private IP address. It cannot be routed on the internet. So normally what happens, you have your private network and you have the public network, which is the internet. So your router will perform what we call NATing. NATing is network address translation. We're going to look at this much later. But network address translation simply maps. It maps public addresses to private addresses and vice versa. So have you understood the difference between private addresses and public addresses? Okay, so let's move on. We have a few addresses that are referred to as special addresses. One of them is called the broadcast address. Broadcast address. The very last address. The reason as to why they are calling it limited is because it cannot go beyond the network. It cannot go beyond this broadcast message. It cannot go beyond the network that it has been created. Because if a broadcast packet goes to the router will discard it. The router will do what? The router is what we're calling the gateway. So the gateway will never forward a broadcast packet beyond the network from which it has been generated. So that's why it's called a limited broadcast address. But otherwise, if a packet has the destination address as 255.255.255.255, then every other computer in that network is going to open up that packet. Is that clear? Now, the very first IP address is called the anycast. Why are they just calling it any? It's supposed to be anycast, if I'm not wrong. Okay, please confirm. Confirm the name, but what I've been knowing is that this is called an anycast IP address. Anycast. So this anycast address, we're going to see how it's used. but generally, it's used to refer to any network. Any network. So when we learn in the afternoon about IP routing, you're going to see one of the implementations of the Anycast IP address, any network, when we configure what we call a default route. Then the other one is called the loopback address. It is the address 127.127.0.0.0/8. So it is used to test the software system. Used to test the software system of a device. By software system, it means it's a virtual interface. When you want to test whether your networking is working, you can be able, for example, to send a ping to 127.0.0 just to find out if the software system for your computer network is working. Are you getting the point? So it's a virtual interface or IP address that is reserved for that testing. Okay, then we have link local, which is link local address, very important, which is 169.254.0.0. Now, I'll just read this. If a host fails to automatically obtain an IP address, then the host can use an IP address block for temporary communication. It can use this IP address block for temporary communication. Now, normally, you can assign IP addresses to computers statically if you configure it static. So any manual configuration. Otherwise, it can be dynamic. Dynamic when you use a protocol called Dynamic Host Configuration Protocol, DHCP. Dynamic Host Configuration Protocol. So what a link local address does is this. You've configured a machine to receive an IP address automatically. But the DHCP server is down. Maybe it has crashed or gone off. So when that happens, your machine can pick one address within this range and use it temporarily. Are we together? So that is what we call a link local address. So don't forget that 169.254.0.0/24. So again, as I said, IPv4 time barred, IPv4 time barred, and that's why exhausted in 2011, as reported by IANA. So they had to create a new one to replace IPv4, one that has a larger capacity. As you can see, IPv4 has, while IPv6 has 28 bits. The address type in IPv4 includes unicast, we've seen. We have broadcast, we've seen. We also have multicast. Among those three, which one is missing? Which one is missing in IPv6? Oh, of course, here we also have Anycast. See, we've seen the Anycast 0.0.0. I don't know why they didn't put it here. It's supposed to be here. So we've seen 0.0, and we've said it's called the Anycast address. But which one is not? Which one is not here that is here? Broadcast, right? So don't forget that we do not have a broadcast address in IPv6. So problem with this one was the depletion, inappropriate packet header design, you've seen the IP header, the way it has so many fields. You've seen all those fields. TTL, identification, fragmentation, blah, blah, blah. With the IPv6 header, it's a little bit simplified. Doesn't have all those fields. Then we know that ARP dependency induced flooding. Oh, okay. We know that, for example, when we are doing ARP request, normally it's a broadcast message. So with IPv4, we have a lot of broadcast messages because of that request. But here with IPv6, we have automatic IPv6 address allocation. We are going to see them when we learn about IPv6, what we call DAD. Okay. So, ladies and gentlemen, I just want us to take a 5 minutes health break. Then we come back and continue. Is that okay? Just 5 minutes. Then we look at subnetting. Okay. So let us continue and look at subnetting. Subnetting. So excuse me, please. Can we? Okay. So subnetting, what can I say? You can think of it as creating subnetworks. Dividing, you can think of it from a very large perspective, dividing one huge network into smaller, more manageable networks. Are we together? In the meantime, just think of it like that. But really, oh, sorry. But really, let's look at this example. When we have a class B network, then that class B network is going to give us 65,536 IP addresses. Are we together? Now, that class B network is going to create one huge broadcast domain. Are we together? Meaning, if we have 200 devices, then we are going to have so many broadcast packets in that particular network, and they're going to occupy bandwidth, consume bandwidth, and reduce service quality. Also, we are going to waste so many addresses, because if we have just 200 devices, whether you rarely get any lab, for example, in a university with such huge number of devices. But if we only use 200 out of all this, are you seeing we've wasted more than 65,200 addresses? Are you seeing that? It's just going to be unusable. We're not using it. So that's the main problem, especially with class A and class B addresses, because they offer huge number of hosts. Class A, 2 raised to power 24. So many. Similarly, class B, so many. At least class C will give us 256. But again, in this lab that we are in right now, we only have 25 computers. So do we really need to waste? We have 254 addresses, valid addresses. So if we only use 25, do we need to use to waste all the others? We don't need to. So that is why we do subnetting. Number one, to reduce the broadcast domain, because we know that anytime computers want to talk, they must start by sending an ARP request, which is a broadcast. So we want to reduce the broadcast domain, and we want to stop address wastage. What happens when the broadcast domain is too large? The internal network is going to be overloaded, congestion. So that's the main problem with these addresses that give us so many hosts. So normally, we might want to divide a network into multiple sub-networks. So that sub-network is what we're calling a subnet. Each subnet is allocated to a separate broadcast domain, meaning when you're on different networks, you must introduce a layer 3 device for you to be able to communicate. And if you send a broadcast packet, the gateway is going to discard it. So you already know that. We know that, right? That if this guy sends a broadcast packet, it will go here, then this guy will simply discard that packet. To not forward it. So for example here, we've broken this up into how many subnets? 1. We have another subnet here, and we have another subnet here. Now, this particular, when you do subnetting, we are doing this through a technology we call variable length subnet mask, commonly referred to as VL, commonly referred to as what? VLSM. You remember when we were looking at the classes, we mentioned what you call the default subnet mask. You remember that? Default, like for class A is /8. For class B, it is /16. For class C, it's /24. So variable length subnet mask simply means instead of using 8, even though it is a class A address, we can use 10 or 12 or 13 or 14 or 15. So that's why we are saying variable length subnet mask and not fixed, not default as per the classes. So that is how we implement subnetting. So let's see through variable length subnet mask. So let's see how we subnet an address. So we just have an example here. So which class does this belong to? Class C, right? Because it's /24, right? 192/24. Just know that is class C. How many total addresses does that give us? Available addresses? Total available addresses. 256, right? Assignable addresses? 250? 254. Now, this can be broken down. Okay, so this can be broken down. Let me just see. Oh, I think it's done in the next slide, not here. Here we're just seeing what we've been able to discuss. That this is the broadcast, this is the network, total IP addresses, and assignable. Instead of available, I prefer the use assignable. Assignable IP addresses is 254. So we've already seen that. So let's see how we can break this into smaller subnets. So we do subnetting by, let's read this together. We do subnetting by doing what? We take bits from the host part. Now, you remember we said that the mask will have a consecutive ones, right? Sindio? The mask will have consecutive ones. Now, and those consecutive ones will represent the network bits, while consecutive zeros will represent host bits. So what we do is that we convert some host bits into network bits. How do we do that? We simply convert a 0, like here, we convert a 0 to a 1. Are we together? So when we convert that 0 to 1, then we affect the number of hosts that this particular address can have. Because now the total number of hosts here is 2 raised to power. Instead of 8, how many zeros do we have now on the mask? See, we've converted one of them to a 1. So we now have 7. So now the number of total IP addresses that we have is 128, all the way from 256. And assignable addresses 126. So when we do that, then that is what we call variable length subnet mask. Now, with that, then this address is going to be written as, let me just write it, is going to be written as 192.168.10.0/20 what? Before it was /24, right? But now we've increased 1. So now it will be /25. So it's now /25. So that's why we are calling it variable length subnet mask, because it's not using the default subnet mask. We've borrowed a host bit and converted it to a network bit. Are we together? Now, when we use variable length subnet mask, in order for you to get the network address and the broadcast address, you now have to use the logical AND. You remember the logical AND that I talked about? So for you to get the network address, you have to do the logical AND between the mask and the IP address for you to get the network address. But anyway, now when we borrow 1 bit, we've borrowed 1 bit, and that is what we're calling the subnet bits. When we borrow 1 bit, how many subnets do we create? When we borrow 1 bit, how many subnets are we going to create from that? 2 raised to power. Are we together? If we borrow 2 bits, then how many subnets do we get? If we borrow 3, we get 8 subnets. Are we together? So for now, we've just borrowed 1. So how many subnets do we get? 2 subnets. 2 subnets. And in fact, one easy way of knowing, for example, the address ranges is simply by doing division. You see, when we have 192.168.10.0/24, how many addresses do we have? 256, right? So if we divide this network into 2 networks, how many addresses do we get? See, still the same thing as 2 raised to power 7. Are you getting the point? Huh? Again, again, for the first subnet, what do you think will be the network address? For the first subnet. And even without doing the AND, what do you think will be the network address for the very first subnet? So it will just be the same address, the same network address as it was for the /24, right? So it will be that first address. Is it making sense? I mean, when it was this, this was the network address, right? And the last one was, the broadcast was 168.10.25/24, right? Now we are breaking this into two networks. So we are going to have two network addresses and two broadcast addresses, right? So for the first subnet, the broadcast, the network address is going to be .0. But this is not very official, by the way. This one is just my thinking because I'm also a mathematician. So the address will be that, right? For the second subnetwork, the address is going to be 168.10.120. Sindio? See, one subnet is giving us 128. So all the way from 0 to 127, right? So the next network is going to begin at 128. So it makes sense. And therefore, if the second subnet is beginning at 128, which one is the last address for this first subnet? 192.10.120 / so that gives you your broadcast address, right? Then this one, 192.168. What will be the broadcast for this one? 255, right? I think so. Okay, sawa. So let's move on. That one I was just mentioning. Calculating the network address. Okay, kumbe it's even here. Anyway, to calculate the network address, you do the logical AND. Are we together? You do the logical AND. For all the parts where we have 255, it's just going to remain the same, right? So you only need to change the last part into binary. Then you do a logical AND of that. So when you do that logical AND, you get all zeros, and therefore the network address is going to be that. For the second subnet, let me see. There's something I'm not saying here. Just a moment. There's something I'm missing. What am I supposed to say? Network address is obtained with all host bits set to 0. There's something I think I'm supposed to say about this, but I can't I can't figure it out. But see, I already told you how to get this. Sindio? So you just add from the first one. The total number is 128. The first one is 0. So the next one, 128. Like that. Okay, so let's move on. If I remember, I'll let you know. Then broadcast. How do you calculate the broadcast? I've already told you how to do that. Let me just see here. Broadcast address obtained with all host bits set to 1, eh? All host bits set to 1. So we simply set all host bits to 1, then we get broadcast. If we change this whole thing, we'll get 127. Then for the second subnet, this bit will be set to 1, then we change all the others to 1, then we get 255. 255. So for the first subnet, this bit is going to be 0. For the second subnet, it's going to be 1. Okay. So I think we have an example here. Let me see. So an existing Class C network segment. Let's see this example. 192.168.1.0/24. Use VLSM to allocate the IP address to how many subnets? How many subnets do we need? 3 subnets, right? So 2 raised to power n must be greater than or equal to 3, right? Sawa. So what will be our n? 2 raised to power what will be greater than or equal to n? Eh? 2 raised to power 2, right? Eh? So 2 raised to power 2 is 4. Yes, you want anything that is greater than, because we need 3 subnets, right? So n here is the number of bits that we are going to to convert from host bits to network bits. Are you getting the point? So it simply means that in order to get 3 subnets, we must borrow 2 host bits and convert them into network bits. So that's exactly host bits. Where is 4 coming from here? Oh, no. You use a network. Oh, I'm assuming I use a network with 10 hosts as an example. Oh, sorry. This thing is I think. Okay. I'm a little bit confused. I'm a little bit confused with the question. I'm a little bit confused with the question and the answer that they're giving. I don't think it's very logical, but I'll just try and explain to you. Forget about the question a little bit, so that I can explain to you this particular example. Let me show you. We have this 192.168.1.0/24. Then we have 3 labs. One lab has 10 computers. Another lab has 10 computers. Another one has 30 computers. So we want to see how can we divide this so that we can effectively use this particular address space. So to do that, we come to this lab. We have 10 hosts. So we know, so far, we know that in order to get the total number of valid hosts, we normally do 2 raised to power n minus 2. It gives us the number of hosts that we want, right? In this case, how many do we want? We want 10. So this formula must give us any number that is equal to or greater than 10. So of course, how to do this? We are going to do 2 raised to power n is equal or greater than 10 plus 2, right? Which will give us 12, right? Which will give us 12. So which number, so our n will be equal to, which number raised to power 2 will give us a number greater than or equal to 12? 4. So our n is going to be 4. Are we together? Similarly, so by 4, it means that we are going to borrow how many network bits? We are going to borrow 4 host bits, I'm sorry. We are going to borrow 4 host bits and convert them to network bits. So that's what we are doing. That's what we are doing here. That is what we are doing here. We are converting these 4 zeros into ones. So when we do that, how many subnets are we going to create from there? We are going to create 16 subnets. And that's why I said, I don't understand this, because they are talking about, I thought it was, I kind of misunderstood this question to mean we find the number of bits that we are supposed to convert or to borrow in order to get 3 subnets. Are you getting my confusion? Eh? When I saw that we allocate these to 3 subnets, I thought they wanted us to find the number or to calculate the number of bits that we need to borrow in order to get 3 subnets. So that is the mistake I had done. But similarly, for 30 hosts, you can also subdivide in order to find n, just like we've done on this 10. So the formula is the same. 2 raised to power n minus 2 is equal to or greater than 30. So that you see, yes. As long as it's mathematically correct, if you want to use logs, it's okay. But I think this is very basic. But I know you can use logs to get n, but some people don't want to hear that maybe. Okay. Yes, you have a follow-up question? No. You really don't need to get exact, because you can't have decimals. You can't borrow 3.2 bits. Am I getting a question? Yeah. So when we want to find n here, we don't want to find equal to 12. We want to get equal to or greater than. But we won't waste so much, because now here we are going to get 2 raised to power 4 total addresses. 2 raised to power 4 is 16, right? Minus 2, you get 14. So if we have 10 hosts, then we are just wasting 4 addresses, compared to 234 that we would have wasted if we didn't subnet this address. Are we together? Yeah. Good. So let's move on and look at another one. Computing subnets. What are we doing here? Please ask. Yes. /28. Yes. Yes, the range. So one of them is going to have 192.168.1.1/28. Another one .2/28. Another one .3, like that. just here. Dot 1, dot 2, dot 3, dot 4, until the last one, because we will already know the range. I think that is what they're trying to show us here. Look here, calculate subnet network address. We want to calculate the subnet network address. Are we together? So we know that we calculate the network address by setting all the host bits to 0, right? Yeah. Then we can be able to find the first subnet and how it's changing. So, oh, sorry. Okay. So the very first subnet will be will be 000, then 001, then 2, then 3, then 4, then 5, converted to binary. Are you getting that? All the way to, if you convert this to, alternatively, once you have the number of hosts, which you know is 16, as we said, you can just add. Are we together? You can add 16, 16, 16 to get the network address of each subnet. See, we've already found that we are going to have 16 subnets, right? And each subnet is giving us 16 addresses. So the first address, the first network address is going to be 0. Then plus 16, plus 16, plus 16, all the way to 240. Yeah, so that is how you find the network address of each subnet. Okay, so that is it with subnetting. I know it's a little bit tricky, but I'm sure if you go through it again slowly, you'll be able to understand it better. So please find time and look at it. In the meantime, let's look at this protocol called ICMP. Allow me to move a little bit faster. ICMP is Internet Control Message Protocol. And normally it's added at the network layer. That is how it looks like. ICMP is very important. It's used to transmit error and control information between network devices. Plays an important role in collecting network information. That's one of the things it does, to collect network information. For example, we're going to be using the ping to do that, to diagnose where problems are, and to also rectify network faults. So the ICMP is very important because it enables network engineers to be able to troubleshoot their network. As we've said, this header is added at the network layer. And ICMP messages have the following fields: the type field, the code field, the checksum field, and the particular message content. The particular message content. Now, the type field is used to store either of these numbers. Then the code field can store either of these numbers. So you can think of the type as the group message, while the code is the specific message. So, for example, in group 3, we have message 0, message 1, message 2, and message 3. That is just an example. So type is the group. So they are grouped because they are similar or they are correlated. So for example, we have network unreachable. So you can get such like a message, meaning that the network is down. Host unreachable, meaning that the host is down. Protocol unreachable, maybe that protocol has been configured so that you cannot be able to access it. Sometimes we block certain protocols like FTP and others in our network. So in case someone tries to access FTP, then they're going to get protocol unreachable message. Port unreachable, maybe if a port has an issue. So I hope you have understood what the type is and what the code is. Now, we also have the echo reply and echo request, which are quite related, because when you send an echo request, what you get is an echo reply. Echo reply and echo request, they're used to test connectivity and also look at information such as the round trip time, as we are going to see. Then the other application that we are going to have a look at of ICMP is what we call ICMP redirect. ICMP redirect, which I'm going to describe to you just now. So just know that under type, you might have maybe 0, code 0, meaning it's an echo reply. Then checksum field. Checksum field is used for to check whether the message is complete for security purposes. Okay. Do you still remember an instance where we said an ICMP message is going to be sent back to the host, to the source? Which instance was that? Yes. Exactly. When the TTL reaches 0. So when the TTL reaches 0, one of these messages is going to be sent. One of these messages is going to be sent. Okay, so let's look at ICMP redirect. It's a very interesting stuff. ICMP redirect messages are a type of ICMP control messages. When a router detects a host has used an optimal route in a specific scenario, the router will send an ICMP redirect to the host, requesting the host to change the route. Requesting the host to change the route. So let's try and understand what they're saying here by using this example. Now, I don't know whether I've mentioned this, but generally, other than the IP address and the mask, the other thing you have to configure in your computer so that it can be able to communicate with computers in other networks is a gateway, right? I think we said this, right? And the gateway simply is the IP address of the egress interface, the interface it can use to go to other networks, right? So for example, this one, we've configured it with 10.0.0.0.100/24, which is this address of this interface. So what happens is, when this guy wants, in this example, this is how it's going. Look here, this guy is host A. This guy wants to send a packet to server A. So what happens? We are on different network segments. How do we know that we are on different network segments? You can see that I'm on 20. I'm on 10.0.0.200/24. But you are on 20/24. So we are on different network segments. So if I want to speak to you, I'll have to go through my gateway. So I'll generate the message, send it to the gateway. Now, if that particular server was on the internet, then this guy will simply send it out to the internet. But this time, this router knows that, hey, if you want to go to the 20 network, then this network is within our local network. It's not outside, it's within our local network. So we don't have to send that packet out, then it comes back. No, we can't do that. So what do? This guy will and that is now the step 2 here. This guy will send a message back to this guy, telling this guy, hey, if you want to go to the 20 network, don't use me as the gateway, use this guy, use RTA. So now this guy is going to use RTA as the gateway in order to get to server A. Are you getting the point? So that is what we call ICMP redirection, because you're trying to use an optimal route to go to server A. The optimal route is you're within us, so just use this other gateway instead of using me as the gateway if you want to reach server A. So that is what is happening here in step 1, 2, and 3, as you can see. Anyone with a question? Okay. Yes, it will dynamically change the gateway address just for that particular connection. Otherwise, if it needs to go to the internet, it will continue to use the default gateway that has been configured. Okay. The other thing that ICMP does is error. Now, the error detection uses the ICMP echo messages in order to check network connectivity between the source and the destination. Now, other than checking connectivity, which is one of the main applications of ICMP echo messages, it also gives other information, such as the round trip time. Now, one of the common applications of the ICMP echo message is an application we call the ping application. So the ping command is used on the network devices on almost all the operating systems in order to test connectivity and reachability, and it uses the ICMP echo message. So in a computer or in a router, you might enter ping, then space, then the IP address of where you want to reach. So why it's called an echo message is because when you send that request, then you receive a reply. So we have an echo request and an echo reply. So what happens is that you're going to get several replies. Like here we have 1, 2, 3, 4, 5. But other than the replies that you're getting, you also get, for example, the time it took for you to get that reply. So that's what they're calling the round trip time. 30 milliseconds, 30, 40. And you also have a summary here. The summary of what was transmitted. So we sent out 5 requests. We got 5 replies. 0% packet loss. You also get the minimum round trip time, the average, and the maximum, so that you can be able to understand, for example, if you have congestion in your network and it's slowing down network services. So that is what we call error, ICMP error detection. The next one is error reporting, very important. ICMP error report. Now, the ICMP error reporting function, the commonly used ICMP error reporting function is what we call the TRASAT. TRASAT is used to trace the route or the path that a particular packet will take to its destination. So ICMP defines various error messages for diagnosing network connectivity problems. So the source can determine the cause for a data transmission failure on the received error messages. So we saw those particular error messages like host unreachable, port unreachable, protocol unreachable, or network unreachable. So, for example, after a network device receives a packet, it cannot access the network where the destination device resides. Then the network device automatically sends an ICMP, unreachable message to the source, destination unreachable to the source. So we've already seen those messages. Anyway, I think someone's mic is bored. Let me just mute you. Okay, so one of the functions is TRASAT. TRASAT is used to check the reachability of each hop on a forwarding path based on the TTL value carried on the packet header. So how does it work? TRASAT is an effective method to detect packet loss and delay. Two things: to detect where you are losing the packet, the particular point, and also any delays you might have, because it also gives you the round trip time. So it helps the network administrators also to discover routing loops on the network. So what happens? Just like the ping, you use the command TRASAT, then the IP address of the destination whose path you want to find out. Now, what happens? This is how it happens. What happens when you send TRASAT from RTA to this particular guy, to that particular guy? RTA will send the first data packet. The destination is 20.0.0.2, but the TTL value will be 1. The TTL value of that data packet, of this data packet, the first one, will be 1. Are we together? So if it's 1, what happens? When this packet gets to RTB, what does RTB does? Decrements that packet by 1, it becomes 0. When it becomes 0, what does it do? It sends an ICMP error message to this guy and discards that particular packet, right? Are we together? Now, when this guy receives this particular error message, it knows, oh, the first router towards my destination is 10.0.0.2. It also knows these times, which are the round trip times, etc., etc. Now, RTA will send a second message, but this time it will increment the TTL to 2 so that it can discover the next router towards that destination. Are we together? So if it sends the message out with a TTL value this time of 2, what happens? It comes here. That color is not visible. I use green. So it comes here. This one decrements by 1, then goes to another router. The other router decrements to 0, sends back a what? An error message. When it sends an error message, then this guy knows, oh, the second router towards my path is this guy. So that's how TRASAT or trace route is used to find the path along which a packet will follow to its destination. So on your command prompt, you can try these commands. You can try ping facebook.com. By the way, when you're using ping and TRASAT, you can also use the domain name instead of just the IP address. So you can try TRASAT facebook.com so that you can see the routers that your packet will follow through until it gets to the Facebook servers. So I hope you remember those applications of TRASAT. So that is it about ICMP. Please remember these 3 functions: error reporting, error detection, and ICMP redirect. Don't forget them. Okay, so now let's see at the basic scenario of ICMP configuration as we finish up. IP configuration. So this is how we configure IP on an interface. Let me change this. Number one, you have to be on which view? Which view is that? User view, system view. You have to be on system view, right? Then you have to type in. You have to type in the. Let me call it keyword. The keyword interface. Then you have to type in the interface type and the interface number in order to go into that particular interface. So now we are on which view? We're on interface view. So, for example, in order to get into this interface, they typed the command interface gigabit Ethernet 0/0/1. So that is the number. So that is how we get into this interface. You can also type this, I think, in short, int g 0/0/1, like that. So once you're there, then you can configure the IP address using the command IP space address, then the IP address, then the mask. You can use the mask or you can use the mask length. Are we together? You can use the mask. Yes? No, this one, right now we are in a Huawei router. This one is a Huawei router. So we are doing this on CLI, on command line interface. So we type IP address 192.168.1.1, then 255. This is what you're calling the mask, .0. So that's one. Otherwise, you can use the length. So that is what we call the length. 24, like that. When you're using the length, you don't use any /. So that's how you can configure an IP address on an interface of a Huawei router. Configuring an IP address for an interface. So this is just an example. Let's go through it very fast. So on the preceding network, where the two routers are interconnected, configure IP addresses for the connected physical interfaces and logical IP address. So I'm going to show you on this actual router what we call physical interfaces. What we call physical interfaces. And also talk about logical interfaces. Now, it's important that we know the difference because we're going to be meeting them once in a while. So a physical interface, as the name suggests, is actually an actual interface that you can connect a particular media on, whether it's fiber or RJ45. So that's what we call a physical interface. Otherwise, we also have a number of logical what? Logical interfaces. So what we're saying is that you can either have a physical interface or a logical interface. A logical interface is a virtual interface. Virtual means you've just created it using the software, but it does not exist physically. Are we together? So a logical interface is a virtual interface. Now, you're going to meet, what we're going to create here is something we call a loopback interface. A loopback interface. Otherwise, as we go on, you're going to meet other virtual interfaces like VIL and IF. Just in the afternoon, we are going to see another virtual interface called null0. We also have other virtual interfaces like tunnels. If we were going to configure VPNs, then you'll create tunnels, and normally they are virtual, logical or virtual interfaces. So these are some of the interfaces. Now, the other thing that I need to mention here is that, and this one is important, is that there are two states. Let me call them states. Let me call them states. There are two states. Is it states really, or I think it's status. So we have what we call the physical status, and we have what we call the protocol status. So this one, it can be up or it can be down. Are we together? Up means on both interfaces, either physical or logical. When the physical status of an interface is up, let me call this interface status. It simply means that it's on. It's on. It's on. It's not down. Down means it's off. Down means it's off. Is that clear? Is that clear? So, for example, on a physical interface, you can, when you connect a physical interface to another device, the status changes from down to up. Are you getting the point? Because now it's connected. But even when you've connected that interface to a particular device, you can use a command called shut to change the physical status from up to down. Is that clear? You can shut down an interface that has been connected. Now, for the physical interfaces, I've told you that. But for the logical interfaces, their physical status is always up. Are you getting the point? When you create a loopback interface or a VLAN if, the physical status is up by default. The other thing is protocol status. Protocol status, the protocol status means that you've configured the interface, e.g. with an IP address. So again, it can be up or it can be down. So if you have configured an IP address on a physical interface, its status is going to be up. It's logical, it's protocol status. If you've not configured, it's going to be down. So I hope you remember that. Now, one thing about the logical interfaces is that they are normally up. They are always up by default. Both the physical status and the protocol status always up by default. So whether you've configured an IP address or not, the protocol status of a logical interface will be up. So,
I have a question, Malim.
yes, please.
On physical status, what are the first? I think physical means something you can see.
No, physical in this sense is not used to mean that. Physical in this sense is used to mean, I think, something like the electrical status. Are you getting the point? Something like the electrical status, because we are saying on a physical interface, when you connect it, then the status becomes up. But even once you've connected it, you can still use the command shut or shut down to disable it.
Okay.
So please let that be clear that physical here does not represent something that you can see. So it's quite controversial, I also feel so. But thank you for raising that up. Okay, now for physical interfaces, we are going to see that you can have what we call a service interface, or you can have what we call a management interface. So service interfaces are used to transmit data. Management interfaces are used to manage the device, that is to configure the device. Are we together? It can be the console interface, or it can be, you can configure any other interface to be a management interface, meaning that if someone is connected to that interface, they can configure the device, for example, via telnet from their office. That's what we call a management interface. Anyway, those are just the theories about interfaces. Now we want to configure these two IP addresses. For G001 on RTB, we give it this IP address, and for RTA on G001 again, we give it this address. Other than that, on RTA, we want to create a logical interface, loopback 0. While here, we also want to create a loopback 0, we give it that address. Now, something else that is important to note here is that loopback interfaces can be assigned a /32 mask. They can be assigned a /32 mask so that it means just that specific address. So it's not consuming any other address. It's just 1.1.1.1, no other address. /32 means that. Okay, so how do we do that? I think I've already typed this and I showed you that on system view, you go into your interface, then you give it an IP address and the mask. Or you can use the number, the mask number, mask length. How do you create a loopback interface? You use the command interface, then loopback, the word loopback, then the number. So you can create loopback 1, you can create loopback 2, you can create loopback 3, etc., etc. So here we're just creating loopback 0. You assign an IP address or configure an IP address in a very similar way towards what you do with a physical interface. Please note that some of the application of the logical interface includes testing, for example, or simulation. For example, you don't want to do another connection. You don't want to do another connection to another router. Then you configure that particular interface. You don't want to do another connection. So you can simply create a loopback interface and give it an IP address. And now you configure your routers here, just these two, then you can be able to ping that loopback address. It means that if you're able to ping that loopback address, then you can be able to simply add another device. Are you getting the point? It's like you're simulating another network that is beyond this router. Eh? Sawa? So that's one of the ways that it's used. Otherwise, some protocols also use the loopback address, and we are going to see, especially when we learn about, for example, OSPF. And the reason why that is so is because the status is always up, and it cannot encounter any problems, loopback address, because it's a virtual address. Interface, I'm sorry, because it's a virtual interface. Okay, now let's look at a case on how to do address planning. This is really nice. I really liked this. This was not there before. So how do we do network IP address planning? So yes. Yes, it's something we're going to do. Yes, we're going to configure both in the lab and also we're going to play around with these devices. So IP address planning must be considered before, considered together with the network structure. Network structure is the topology, right? Are we together? Then also routing, protocols, traffic planning, and service rules. So these are some of the things that we plan. So you can look at my HCIP videos to see, to get more information on how this is done. So in addition, IP address planning should be corresponding to the network hierarchy or the network structure, and it should be performed in a top-bottom way. So the network hierarchy, core, aggregation, access, like that. So in conclusion, IP address planning objectives are, number one, to achieve easy management, then easy scalability so that you can be able to add new devices easily, and also achieve high utilization. So this is an example, an IP addressing example. So the background, we have a company which has been assigned the address 192.168.0.0/16 as the network segment address. So how can we be able to plan this? One way we can do it, for example, is to divide or subnet this particular network in terms of the service types or departments. So for example, here, we are simply looking at the departments we have, for example, R&D, marketing department, admin, and then we also have guests, etc., etc. So what we do is that we subnet this particular address, and we ensure that these addresses are contagious, meaning they're just following each other in a very structured way, so that you can offer easy management. You can achieve easy management of the addresses. What that means is when you see this IP address, you just know that, hey, then this is coming from the R&D department, for example. And it also achieves easy scalability, because next time you want to add another department, you simply add .5, 192.168.5. .0/24. So that is how we plan for the IP. Now, some of the rules that we use during planning is, number one, uniqueness. Uniqueness simply means that every host in your network should have a unique IP address. And then continuity. I think we've already seen continuity from .1 to .2 to .3 to .4. Continuity is also important because it is used in what we call route summarization. So in the next topic, we are going to learn about route summarization and why it is important. Of course, also scalability, as I've said. If you want to expand, you go to .5, you go to .6, and so on and so forth. Then it also gives a structured, it also gives a structure, a clear structure of how data flows in your network. And you can be able to configure so that now data priorities are set based on the service that a particular person uses, using what we call the quality of service. You remember the field we saw on the IP header? What was the name of that field that was used for quality of service? Yeah? Yeah? Yeah. Okay. Okay. So, ladies and gentlemen, thank you very much. Thank you very much for your patience. Please take time to discuss these two questions. And in case you have a question, you can let me know. You can let me know. Asanteni sana.